Um, Before that, I need to ask you about the previous some questions from the previous classes, and I'm informing you that our classes are maybe found in YouTube also. That is uploaded by Ajim. So if you have any doubt, you can listen it again. But class is important most because this is a two-way communication. You're directly talking with your teacher, and you can express what you didn't understand. But if you have any doubt, you can go through with the YouTube video, which will be uploaded after the class. And this video is recording. This class is recording, so you'll get it in the channel. Ajim, please say your channel name, please. Okay. So this is the channel, and after some times I made this pH. Who can say what is pH?
Negative logarithm of H plus.
Hydrogen ion concentration. Yes. What is
Negative
pH scale
logarithm
then?
of
What is pH scale then?
Sir, it is an arbitrary logarithmic scale having the range of pH that covers the practical range of acidity and alkalinity in commonly available solutions.
Yes. Do you have a product in this definition? Do you know what is the product in this definition?
Sir, the end result of a reaction.
Multiplication.
It is the multiplication. Okay, not the end result. Multiplication. Biological importance of law of mass action. Who can say the biological importance of law of mass action? The doc. Do you see? As I said, as mnemonic.
Sir,
Anyone?
determining H. Sir, determination of H plus concentration in pH.
Yes. Then
Sir, determination
of
of Anderson-Hasselbalch equation.
yes. Then
Pairing unknown substances.
hmm. Okay. To the next class. Buffer. So buffer. What is buffer? Uh, we have gone through this or not? Yes, we have gone through this. They say what is buffer?
Ability to resist pH change.
This is a mixture mainly. Okay, the solution or mixture of weak acid and their conjugate bases, mainly weak acids or their conjugate bases, or maybe the weak base or their conjugate acids, both mixture. Okay, which have the ability to resist a change in the pH. If you have more pH, then it decreases the pH by its acid solution in the mixture. And um, if pH level decreases, then it's increases your pH by its base solution. Okay, because it has both acids and base. Both are called buffer. They if they have weak acid and conjugate base, then it also called buffer. And if it has weak base and their conjugate acid, this is also called buffer. So what minimize your changes in the fluid, in the body fluid, minimize the pH changes in the body fluid. This is the buffer. So, which have the ability to resist a change in the pH following addition of a moderate amount of strong acid or base. This is called buffer. This is the definition from the Harper 13th edition. And a buffer is a substance that has the ability to bind or release proton in solution, thus keeping the pH of solution relatively constant despite the addition of considerable quantities of acid or base. This is from the Ganong and others also. You may, yeah, you will say from the Harper, because Harper is the textbook of biochemistry. Ganong is textbook of physiology, but you will say appropriately from the Harper. Okay. So what are the components of buffer? As I said in the definition, what are the components of buffer? Can you
Weak
say?
acid and their conjugate base.
Weak acid and their conjugated
Their
bases.
conjugate base and weak bases and their conjugate acids.
Yes. So you can say a weak acid and a salt, that is the conjugate base, or which is formed by the weak acid and a strong base. And can a single acid or base act as a buffer? You can say.
No,
No,
sir.
sir.
No,
No,
sir.
sir.
Why?
Sir, because buffer is a solution or a mixture of weak acids.
Yes. Whenever you have any doubt, you will go to the definition. As I said, you will go to the definition. Always, um, always apply this technique throughout your medical life. Always. Whenever any doubt, you go to the definition of that word. In definition, we have said that this is a mixture. So singly, it cannot buffer any solution. Like you know, a single acid or base cannot act as a buffer. Buffer is always a mixture. That is the answer. So write down the importance of buffer. It always comes in the written part. What is the importance of buffer? You can say.
Determination of pH.
You can say what? What? Sorry. Say it again.
Determination of pH.
Not determination of pH. Determination of pH. Yes, determination of pH is one. But maintaining the optimum pH is the main activity. And also by maintaining this optimum pH, they maintain the optimum enzyme activity. So buffer maintains the pH of the body fluid constant. As we know, it is the homeostasis. Regulation of neutrality also important. In they regulate the neutrality of the body within a relatively narrow limit of the pH, compatible for the life of the most cells. They used for making standard solution of constant pH. Anything else? Who can say? Who can say anything else? They are used to maintain a given pH concentration necessary for the optimal activity of a reaction. As I said, buffers are used in the laboratory also. For what? You can say.
Sir,
Buffers
growth
uses in lab
microorganism.
to,
Microorganisms.
yes, for the growth of the microorganism, because they are cultured in in the lab to create some of the medicines or to research on them, to do some research on the microorganisms. They need to be cultured. So they are cultured in a media, and that media need to be maintain an optimum pH to for the survival of those microorganisms. So buffers are used to maintain the optimum pH on those culture media. Am I clear here up to this?
Yes, sir.
Okay. Then classify buffer with example. Who can say classification of buffer? That is the blood buffer. In blood, as we know, there is plasma and red blood cell. Buffers are lies in those, remains in those. So in plasma, the bicarbonate buffer is the most important buffer, and in RBC, the hemoglobin buffer is the most important buffer. Hemoglobin and oxyhemoglobin buffer. So you will say in BPP as in plasma bicarbonate buffer, plasma protein buffer, and phosphate buffer, and in RBC hemoglobin buffer, oxyhemoglobin buffer, bicarbonate buffer, and phosphate buffer. As you can see in the next slide, that we have all those bicarbonate buffer, plasma protein buffer, and phosphate buffer. But in we are saying it as a consequent basis, or saying it in a chronological basis, because the which buffer is in greater ratio in plasma and RBC is situating at the first. So in plasma, bicarbonate buffer is the mostly found buffer, so bicarbonate buffer, and in RBC hemoglobin buffer. You will find bicarbonate buffer, and then protein buffer, and then phosphate buffer, BPP. And in intercellular fluid you will get it PPB, that means protein buffer, then phosphate buffer, then bicarbonate buffer in intercellular fluid. Oh,
So, and its function
sorry,
human cell.
sorry. Ammonia buffer, phosphate buffer, APB, and bicarbonate buffer. And buffers from the respiratory system like a hemoglobin buffer, oxyhemoglobin buffer, and bicarbonate buffer in the respiratory system, because they are mostly volatile acids. Volatile acid means, what do you mean by volatile acids? What do you mean by volatile acids? Can you say?
The excretion through lungs.
Yes. Who gets expelled out by the lungs as a as gases? They are called volatile acids, and others gets expelled out by renal system.
Renal.
So differences against changes in the proton in ion concentration, we can say, um, please show the next slide, please. So that's all the classification of buffers and body buffer system. Important body buffer system, if you are asked, you will say bicarbonate buffer first, then hemoglobin buffer, then protein buffer, then phosphate buffer, then ammonia buffer. Differences against changes in the proton ion concentration. If you have proton ion concentration more, then what will happen? pH will increase or decrease? Who can say? If you have proton concentration more in your blood, then what will happen? Your pH will decrease or increase?
Sir, pH will decrease.
Decrease.
Decrease. Increase.
Who is saying increase?
Decrease.
Okay, who is saying decrease? Please explain.
Sir, if there is more H plus ion in a solution, then it will become acidic solution, sir. So, sir, the pH will decrease.
Exactly. The explanation is this. So, as pH is the negative logarithm of proton ion concentration or hydrogen ion concentration, so when the pH level it acts inversely with the proton level. When proton level increases, pH level decreases. When proton level decreases, pH level increases. That is the simple equation. So don't be confused. Defenses against changes of proton ion concentration. So when your pH level is decreasing, that means the condition is called acidosis. Acidosis in your body. So buffer will react on this and try to maintain your pH level. So buffers, lungs, and kidneys. There's three primary systems that regulate the pH. There's three regulatory system maintains the pH of the body fluid to prevent acidosis or alkalosis. The chemical acid-base buffer systems of the body fluids, which immediately combine with the acid or base to prevent excessive changes in the proton concentration. Do you understand this?
Yes, sir.
Okay. The respiratory center, which regulates the removal of the carbon dioxide and therefore carbonic acid mainly from the extracellular fluid. So respiratory center also regulates the pH by removal of the carbon dioxide. And the kidneys, which can excrete either acids or alkaline urine. When you have more pH, that means you have alkaline urine, and by urine you can excrete all those alkaline solution in your body. And if you have more acids in your body, you can excrete acidic urine from your body. That's how they maintain the pH also. So whenever a patient comes with acidosis or alkalosis, we give them diuretics. Do you know what is diuretics? I said in the previous class.
ADS.
Do you know what is diuretics? Anyone?
ORS.
The drugs which makes more urine, okay? More urine. That means when you're giving a diuretic, the patient will ureate more. Patient will create its urine in his body. So when you have acidosis or alkalosis and you are giving diuretics, it will excrete your body's excess acid or alkaline solution through urine. So buffer is maintained by this process. So diuretics are important. You will see in your pharmacology subject in the third phase of medical science in this curriculum, diuretics and all those medicines. Okay, so that's how defense against changes of proton ion concentration is maintained. Physiological buffer. These are the buffers present in the body and maintains the pH of body fluid at a constant level despite addition of acids or bases during the normal metabolic activities in the body. Bicarbonate buffer, protein buffer, and phosphate buffer.
Sir, what is the
Yes.
example of diuretics? Examples?
Example of diuretics is like you can say there's a lot of diuretics. Thiazide diuretics. You can say spironolactone is a diuretics.
Sir, most
These
commonly
are
used.
the most commonly used spironolactone. You can say thiazide diuretics are also. These are the groups, lots of groups. You don't need to about the group in this phase. It is evident that blood pH 7.4 and the ratio of bicarbonate to carbonic acid is 20:01. Thus, the bicarbonate concentration is much higher. That means 20 times than carbonic acid. The carbonic acid is only 0.1. So in the blood. This is referred to as alkali reverse and is responsible for the effective buffering of proton ions and generated in the body. Main element of okay, if you get disconnected, you will join faster again, inshallah. Um, so how many minutes are left? Okay. So at a glance, if comparison between the ECF and ICF buffer, main element is bicarbonate in ECF and ICF has protein and phosphate buffer. PP, you will remember PP, protein and phosphate buffer is in ICF, and ECF. As always, I taught in the previous class that ICF is always maintaining its negativity inside and positivity on the surface of the cell outside. You know, so inside proteins and phosphate, all those are negative contents, so these are inside the ICF. And buffering capacity is moderate in case of ECF and large buffering capacity in case of ICF because it's need, and response is quick in case of ECF and slow in case of ICF. Everything is works for the to maintain the homeostasis mainly. Effect on the serum potassium level, no effect in case of ECF buffer. Serum potassium level has no effect, and altered serum potassium level has effect on the ICF buffer. So that's all for the comparison. And at a glance, body buffer system, you have bicarbonate buffer, phosphate buffer, protein, hemoglobin, and ammonia buffer. Weak acid in case of bicarbonate buffer system is carbonic acid. Conjugate base is bicarbonate ion. Working site is mostly ECF, and pK is 6.1. That table is must needed. Must remember the table. Body buffer systems. You can see the table. Can you see the table?
Yes, sir.
Yes, sir.
Oh, oh. Please show the next slide, please. There is nothing important in this slide. Please show the next slide, please. Next slide, please. Okay. So how the buffer acts? Mechanism of buffer action. This is the most important question in this buffer system. How buffer acts? Frequently asked in the written. Here you can see write the mechanism best in the following ways. Like first of all, it does conversion of strong acid into weak acid. Conversion of strong acid into a weak acid. And number two, conversion of strong base into weak base. There's two type of steps: conversion of a strong acid into weak acid and conversion of a strong base into weak base. When a strong acid is added to a buffer solution, that may, for example, by bicarbonate buffer is it is neutralized by conversion into a weak acid. Strong acid like hydrochloric acid and sulfuric acid, if you add sulfuric acid and hydrochloric acid, you need bicarbonate buffer, and it is neutralized by conversion into weak acid. Example, you can see the equation: hydrochloric acid is dissociates as a strong acid into hydrogen ion and chlorine ion, and carbonic acid is dissociated into proton and bicarbonate ion, and it is forming the carbonic acid. Because the proton comes from the hydrochloric acid, it attaches with the bicarbonate buffer. So buffer is acting here. Bicarbonate buffer, that means as strong acids when dissociates into the body fluid, it dissociates into ions, hydrogen and fluorine. It gives a proton. That proton is taken by the buffer, negative buffer solution, negative bicarbonate buffer. That means it is forming the carbonic acid. That carbonic acid is a volatile acid that is expelled out by your lungs or by kidney. So this is the weak acid. Carbonic acid is the weak acid. So from a strong acid, it is converting it into a weak acid, that is the carbonic acid. Thus, added proton is tied up in carbonic acid. So there is no increase in proton concentration, and as a result, no change in the pH occurs. So conversion of strong base into weak base. How this occurs? When you have increased level of base in your body, that means alkalosis occurs. Previously, we have a conversion of a strong acid into weak acid. That means when you have acidosis, how buffer reacts, and when you have alkalosis, how buffer reacts. When a strong base, that means sodium hydroxide, is added to a buffer solution, bicarbonate buffer, like bicarbonate buffer, hydroxyl combines with a proton to form water. You can see the example: strong base, that is sodium hydroxide, convert dissociates into sodium and hydroxyl in your body fluid, and hydroxyl and also carbonic acids in case of bicarbonate buffer system. Bicarbonate buffer system has carbonic acid which dissociates into proton and bicarbonate. So proton of the carbonic acid, that means weak acid, and hydroxyl ion of the dissociated strong base is attached together and water is formed. But the proton concentration is decreased, which can increase pH. So more carbonic acid dissociates into producing proton, and thus there is no decrease in proton concentration, and as a result, no change in the pH. Am I clear here?
Yes, sir.
Yes, sir.
Then maintenance of pH. So whenever you are asked in the mechanism of buffer action, you will say these 2 points. And how body pH is maintained: by blood buffer system, respiratory system, and renal system. This no need to explain, because the blood buffer system is the first line defense, and acts within a second. They acts within a second. That's why they're called first line defense. The base component of the buffer combines with the free proton of metallic acids and metabolic acids, and is converted into the weak acids, which dissociates very little. Thus, buffers prevent abrupt pH change. The buffer base plus from the metabolic proton from the metabolic acids, both forms weak acid, that for example carbonic acid, like bicarbonate buffer and proton. All these are same thing is there, as we explained in the mechanism of buffer action. Respiratory system, how does? Respiratory system is the second line defense and acts within minutes. Blood buffer acts within seconds, respiratory system acts within minutes, and third line defense, that is renal system, that acts within hours to days. Renal system needs more time. So acts within minutes, and there is regulation of carbon dioxide concentration by the respiratory system. Lungs excrete volatile acids, as I said. Carbonic acid is in the form of carbon dioxide through the respiration. And renal system, as a third line defense, it regulates the plasma bicarbonate concentration by the kidneys, and this occurs by reabsorption of the filtered bicarbonate, a generation of the new bicarbonate, and excretion of the non-volatile acids, because the volatile acids are already excreted by the lungs, but non-volatile acids, how they will excrete? By the renal system. So reabsorption, this is called reabsorption, because in case of filtering, it absorbed and absorbed, it excrete, absorb, and reabsorb again in the nephron. That's why it is called reabsorption, because filtering again. So reabsorption of filter filtered bicarbonate in the renal system, and generation of new bicarbonate and excretion of non-volatile acids in the renal system's third line defense. That's how they regulates plasma bicarbonate concentration mainly. Please show the next slide, please. Next slide, please. Buffering capacity is maximum when there is an equal amount of acids and bases are present in the system. So buffering action is maximum when pH equal to pK. So the question is, why buffer capacity is maximum when pH of a medium is equal to pK? That means dissociation constant, negative logarithm of dissociation constant. So it's equal to pH when the maximum capacity, buffer capacity is maximum when the pH is equal to pK. Just we need to prove it, and why we have to explain it. So buffering capacity is maximum when there is an equal amount of acid and bases are present in the system. Now we see the Henderson and Hasselbalch equation. As we know, pH is equal to pK, dissociation constant, plus log salt modulus divided by acid, salt divided by acid. So if the concentration of the salt and acid are equal, that means that there will be one only. So log will be 0 here, including log, it will be 0. The equation will be 0. Log 1 equal to 0. So in that situation, pH is equal to pK. So we can say that the buffering capacity is maximum when pH is equal to pK. Do you understand, guys?
Yes, sir.
We can prove this by this following example. Like suppose a buffer solution contains this amount of solution, this amount of this amount of ethanol, 16 ml, 0.5 mole sodamide, and 4 ml, 0.1 mole ethanol. Its pK is 5. The pH of solution will be pH equal to pK plus log 16 by 4. How they got 16 by 4? Because 16 ml and it is 4 ml. 16 by 4. That means 5 plus 0.60 is equal to 5.60. Here pH is not equal to pK. So now it is not maximum capacity of buffer. Now suppose 1 ml, we need to make it as a maximum capacity. So now 1 ml 0.1 mole hydrochloric acid is added to the buffer. This will convert 1 ml 0.1 mole ethyl sodium into 1 ml 0.1 mole ethanol, and the pH of the solution becomes pH equal to pK plus log 15 by 15, 15 by 5. That is equal to 5 plus 0.477 equal to 5.477. So decrease in the pH by ACl is 0.123. Now suppose another buffer solution containing this. So the pH of solution is 10 by 10, log 10 by 10 equals C. So 5 plus 0 is equal to 5. So pH is equal to pK. Whenever the pH is equal to pK, that means the capacity, maximum capacity of buffer solution. We see that the buffer solution having pH equal to pK, that prevents pH changes very effectively. We don't need these questions in case of written or viva, but just try to understand all those for one time. You don't need in the written or viva, not necessary, because math is not always will not always come in the biochemistry. Sometimes you need math in the nutrition part chapter. You need some of the math. Otherwise, math is very little. Write down the criteria of an ideal buffer. Please show the next slide. Criteria of an ideal buffer is pK will be closer to pH. As we know, pK is equal to pH. That's why I discussed about the maximum capacity, because criteria of an ideal buffer is when pK will be closer to pH. Maximum will be pK is equal to pH. So buffering capacity must be higher. Ideal buffering capacity must be higher. The salt part will be slightly higher than the acid part. That is the 3 point of criteria of ideal buffer. Bicarbonate buffer component, you can see component of bicarbonate buffer, pK value 6.1, action, how they act, linking functions, site of action in the kidney, and effective in what? Mild acidosis and alkalosis are. Mild acidosis and alkalosis, we need bicarbonate buffer. Site of action in the kidney is proximal convoluted tubule. You will learn in the renal system what is proximal convoluted tubule. You have gone through in a higher secondary level with the nephron, isn't it?
Yes, sir.
Didn't you? Nephron has proximal convoluted tubule. Did you gone through with this?
Yes, sir.
So you know the PCT, that means proximal convoluted tubule, and thick ascending segment of the loop of Henle, and early distal tubule, and intercalated cells of the late distal and collecting tubules. So all these are part of the nephron. Site of action occurs in this part of the nephron. This bicarbonate buffers action. Function is acidification of the urine, as well as bicarbonate buffer system serves as an index of understand the disturbance in the acid-base balance of the body. So you have acid-base balance disturbance as bicarbonate buffer is activated, and it gets signal. It try to give you the signal that your body buffer system is altered. So acidification of urine is needed, because when you get the acidified urine, that means your body acid will be decreased, because urine is part is the thing to excrete. Why bicarbonate buffer system is the most important buffer in the body? This is most important also, one of the most important questions. Why bicarbonate buffer system is the most important buffer in the body? Bicarbonate buffer is the most important buffer in the plasma, because the two elements of the bicarbonate buffer system is bicarbonate and carbon dioxide are regulated respectively by the kidneys and lungs, because you can excrete carbon dioxide by the lungs and bicarbonate by the kidneys. As a result of this regulation, as two system affecting is effectively regulating this buffer system, pH of the extracellular fluid can be precisely controlled by the relative rate of removal and addition of the bicarbonate by the kidneys, and the rate of removal of the carbon dioxide by the lungs. So two system actively working in this buffer. So if you use bicarbonate buffer, it will be quicker to maintain your pH. Bicarbonate buffer is present in the plasma at higher concentration than other buffer system. So it is also, that's why it is also important. In metabolic alkalosis, that means when there is excess level of bicarbonate and excess and less proton in the blood, bicarbonate is neutralized by proton in renal tubular lumen. But there is excess amount of bicarbonate in the renal tubular lumen, which lost in the urine as free form as alkalosis is corrected. You can see the picture here. The renal tubular cells, renal interstitial fluid, and tubular lumen here. You can see sodium and bicarbonate. There is exchange pump in the cell. You can see the sodium potassium pump with the ATP energy. You can see I taught you in the physiology class the cell junction and the active transport system. Sodium potassium pump, you can see in the picture. Sodium potassium pump, and there is exchange pump of sodium hydrogen pump. Exchange pump, sodium is in getting inside, the hydrogen getting outside, and there is carbonic acid dissociates into hydrogen and bicarbonate, where the bicarbonate going out, and sodium also going out. So this is the co-transport method. And you can see carbon dioxide also coming and going out also. So this is the mechanism of actions of how bicarbonate buffer act. Am I clear here, guys?
Yes,
Any
sir.
doubt?
No, sir.
Okay. Show the next slide, please. Different blood buffers, yes. So different blood buffers, importance of different blood buffers or function of blood buffer in the acid-base balance, maintaining normal pH. During metabolic activity, body produces both volatile and non-volatile acids. The volatiles are like carbonic acid and non-volatiles are like biphosphate and bisulfate acids. Volatile acids are excreted via lungs and non-volatiles are excreted via kidney, as you know. But before their excretion, they may decrease the normal pH. During this time, buffers absorb the proton and prevent the change in the normal pH. As in case bicarbonate buffer acts within seconds, and they are the first line defense, as you know, but they can't eliminate proton from the body and only keep them tied up until the excretion of the proton via lungs and kidney. Thus, buffers maintain normal pH for acid base balance. Am I clear here?
Yes, sir.
Okay, now name some of the buffer mixtures. Can you say the name of the some of the buffer mixtures? The glycine and hydrochloric acid, acid potassium phthalate and hydrochloric acid, acid potassium phosphate and sodium hydroxide, sodium bicarbonate and sodium carbonate. These are the buffer mixtures. If you are asked about the sum of the buffer mixtures, you may say this things. So difference between the bicarbonate buffer and phosphate buffer, you need to learn. We'll go through this. One of the important table, bicarbonate buffer and phosphate buffer difference. Let's go to the next slide, please. There's nothing important here. Next slide, please. All those table of difference between the different buffer. Okay. pK. pK is the negative logarithm of dissociation constant, as we have gone through this definition. pK is equal to minus log k, and k is the dissociation constant, as you know. Give the pK of the body buffers. If you want to know the pK of the body buffers, so bicarbonate buffer has 6.1. That is the most important. You cannot forget this. Phosphate buffer 6.8. Protein buffer 6.6 to 7.9. You need all these ranges. Oxidized hemoglobin buffer 6.8. Reduced hemoglobin buffer 7.8, and ammonia buffer 9. So increasing one by one. pK. So indicator and titration now. Indicator you have gone through with the indicator and titration in the HSC level, higher secondary level. An indicator may be defined as a weak or sorry. Now, am I audible here?
Yes, sir.
Yes, sir.
Okay. So indicator as the indicator may be defined as weak organic acid or base, which changes in color or ionization with the change of the pH of its aqueous solution, and thus indicates the end point of an acid-base reaction. So if all those table, this is not necessary actually. No need. Just go through with the definition indicator. You may ask in the your item, and what is indicator, and you may be asked in the item about the color changes also. Methyl orange has orange to yellow color change, and methyl red has red to yellow color change, and phenol red, so yellow to red color change. Phenolphthalein has colorless, and if it as it is colorless, it goes to red color, changes into red color. So these are the color change. So just example of this is and definition from the indicator part. Please go to the next slide, please. Uses of indicator, you may go through just reading uses of indicator if you are asked by your external somehow. It is not so important. Please go to the next slide. Next slide, please. Ajim, next slide, please. Okay, define titration. That definition is important here. And role of indicators and in titration. This is important. In titration, an indicator gives a sharp color change when an equivalent amount of standard acid and alkali has been added, and this color change indicates the end point of the titration. What is the titrable acidity? It is the amount of total ionizable hydrogen, both ionized and non-ionized, and this is determined by the titration against a base. And the titrable acidity of a solution is measured by reacting the acid's presence with a base such as sodium hydroxide to a chosen endpoint close to neutrality as indicated by an acid sensitive color indicator. This is not important all, just what is titrable acidity, go through with this. Short note of titration comes in Russia University, but when a short note comes, you will give the definition, the roll up indicator, and an example is in short. You will give the example in short. Okay. Now the most important part, solution. This is important. So this concentration again. Solution, crystalloids. These are important parts. Define solution. A solution is a homogeneous mixture of two or more substance. Homogeneous mixture of two or more substance, not heterogeneous. Homogeneous mixture of two or more substances which has no definite chemical composition at a definite temperature and pressure. Is it clear about the solution?
Yes, sir.
As you have gone through the solution in the higher secondary level also, didn't you?
Yes.
Yes.
Sir.
Okay. So classify the solution. One of the basis property of or characteristics on the basis of the property or characteristics, on the basis of concentration, on the basis of their saturation, and on the basis of permeability, on the basis of tonicity, on the basis of solvent. Some lecturers gives their classification of solution personally. They may give some of the professor, but standard uh, solution classification is this on the basis of property, qualitative, and quantitative. Qualitative are not measurable, and quantitative are measurable by quantity. On the basis of concentration, normal solution, molar solution, osmolar solution, and percent solution. Normal, molar, osmolar, and percent solution. On the basis of their saturation or physical appearance, ultrasound solution, unsaturated solution, and saturated solution, saturated, unsaturated, and supersaturated solution. So USS, that means unsaturated solution, saturated solution, and supersaturated solution on the basis of saturation. On the basis of permeability through the cell membrane, colloidal solution and crystalloidal solution. Some solution have permeability to the cell membrane, colloidal. They're called colloidal solution, colloid, and crystals. That is crystalloid solution. They are also permeable through the cell membrane. On the basis of tonicity, we have isotonic solution, hypertonic solution, hypotonic solution. These are mostly asked. What are the on the basis of tonicity? Because they are mostly needed in case of practical patient. In case of practical life, you need this solution: isotonic solution, hypertonic solution, and hypotonic solution. Normal saline, you can see in the hospital, which is given to the patient by intravenously.
What is the meaning
Which
of
solution?
anesthetic?
Sorry.
What is the meaning of tonicity?
Tonicity, that means that is the tone, that is a tone or concentration maintains as similar to the plasma, so isotonic means it is as similar to our body plasma, and hypertonic means its its osmolality is greater than plasma, and hypotonic means its osmolality is lesser than plasma. So isotonic, hypertonic, and hypotonic. Okay, like plasma solution has 300 milliosmol per liter osmolality, and normal saline, which is given to a dehydrated patient through intravenously, this is almost similar to the about 307 milliosmol per liter. And we have Hartmann solution that is also given in a patient, burn patient in hospital. That is also isotonic solution. So hypertonic, isotonic, and hypotonic. On the basis of solvent, aqueous solution, non-aqueous solution. On the basis of method of preparation, simple solution and complex solution. So most important is on the basis of tonicity. Please show the next slide, please. You can see the diagram properly. This diagram will show you qualitative and quantitative solution. Colloid and crystalloid are qualitative, and in colloid there is emulsoid and suspension, and quantitative has standard solution and non-standard solution. Standard solution has these are the classification on the basis of property mainly. Standard solution has normal, molar, molal, osmolar, and percent solution. Percent solution has weight divided by volume, weight by weight, and volume by volume percentage. So non-standard solution has unsaturated solution, saturated solution, and supersaturated solution. Non-standard. We use mainly standard solution in our OT, in our operation theater, in our hospital, in hospital bed. In a dehydrated patient, we use standard solution. Normal, molar, molal, osmolar. We'll get all the definition next, inshallah, one by one. Molecular weight of any compound. Molecular weight of any compound means the atomic weights of component elements in their proper proportion in that compound. Molecular weight is obtained by adding the atomic weight of a component element. Molecular weight of sodium chloride is 58.5. Here, atomic weight of sodium is 23, as you know. Atomic weight of chloride is 35.5, very famous atomic number. And molecular weight of sodium chloride is 58.5. So these are the molecular weight. Gram molecular weight. What is the gram molecular weight? Can you say? What is the gram molecular weight? You have gone through in a higher secondary level all those definitions.
Sir, the weight of an element compared to 1 gram of hydrogen.
Kind of, but there is updated definition also. Gram molecular weight you can define by expressed in you can express in details, like, or express in more professionally, like molecular weight expressed in gram is known as gram molecular weight. As gram molecular weight of sodium chloride is 58.5 gram. So when you are expressing as gram, not for only hydrogen, whenever you are expressing as gram, this is called molecular weight, gram molecular weight mainly. So you can as you have learned, it's 1.008 gram of hydrogen. So this is, you can say, equivalent weight of an element, like molecular weight divided by valency. You can express by this. Solute. What is solute? A solute is a substance which is dissolved in the solvent and loses its physical state to form a solution. In a word, the dissolved substance in the solution is solute mainly. Sugar, sodium chloride, all dissociate, dissolves in solution. And what is solvent? A solvent is a substance which has capability to disperse another substance in a solution and has the same physical state as that of the resulting solution. In word, the medium that dissolves the solution is solvent, like water. Define normal solution. This is the most important question here. You must be asked. Normal solution. It is a solution in which 1 gram equivalent weight of the solute is dissolved in 1 liter of solution. Are you clear?
Yes, sir.
What is normal solution? It is a solution in which 1 gram equivalent weight of solute is dissolved in 1 liter. You have 1 liter solution, you dissolve 1 gram of solute, that is the normal saline. Normal solution. Normal saline also made by this. 1 gram equivalent, for example, 1 gram equivalent hydrochloric acid is 36.5 gram. Therefore, as normal solution of hydrochloric acid contains 36.5 gram of hydrochloric acid in 1 liter solution. Another example is 1 gram equivalent weight of sulfuric acid is 49 gram in 1 liter solution. Define normal saline. What is normal saline? This is mostly asked also. Normal saline, as I was saying, the most needed thing when you are in operation theater or when you are in a hospital bed, you need this normal saline to maintain your body fluid. 0.9% sodium chloride solution is called normal saline. Clinical uses of normal saline. This is also important. As I was saying, clinical uses of normal saline. Normal saline is very important fluid of excellent utility. That is more effective. Utility means effective. Daily this replacement of sodium requirement like 500 milliliter per day. We need sodium for 500 milliliter per day. If you lose more of the sodium, you need daily replacement by this saline 0.9% sodium. As you are losing more sodium and potassium level by dehydration or diarrhea or vomiting, you need sodium chloride to replace it. Essentially, during intra and post operative periods, you need also this normal saline. Intra means intra operative period means during operation and before operation, and after operation you must need. After means post. So post operative period you need also this normal saline. In 5% dextrose, that means DNS, 5% dextrose in normal saline, 5% DNS also need normal saline to mix it. 5% dextrose in normal saline. So normal saline is needed also here to make a DNS solution. Replacement of sodium and chloride. Vomiting due to the GIT, as I was saying, vomiting due to GIT infection, food poisoning, intestinal obstruction, gastric outlet obstruction, all those things. If you have vomiting, you need to replace sodium chloride solution, 0.9% sodium chloride solution. That means normal saline. Fluid and electrolyte loss due to the gastric, duodenal, or intestinal aspiration. You need a bag of 0.9% solution in normal saline. Washing purpose. Please go to the next slide. For washing purpose, you need stomach wash, urinary bladder washing through the catheter. In case of operation theater, if you are a surgeon, you need to wash stomach when you after the operation, after before closing your abdomen or closing the operation field in the body. You need to wash out all those, and you need to wash stomach before taking the patient to the operation theater, because you need to operate a clean stomach, or you need to operate a clean abdomen before clean abdomen if you want to open an abdomen. Urinary bladder washing through the catheter. So there's all things needs 0.9% sodium chloride solution saline. That means normal saline. Thorough peritoneal toileting. Peritoneal toileting is done. Washing is done by normal saline. Washing of any injured area or burn is also need normal saline. So you can't run a hospital or you can't run a emergency system, medical system, without normal saline. Continuous irrigation of urinary bladder after TURP, that means transurethral resection of the prostate or prostatectomy. This occurs in case of a patient which have benign enlargement of prostate. This is a disease, benign enlargement of the prostate occurs, sometimes benign and sometimes maybe malignant. That means cancerous maybe occurs. Um, every male has a prostatic organ that as an organ that is called prostate behind behind the penis or behind the genitalia. There is a prostate. So prostate may be enlarged after 40 to 60 years. This enlargement of the cells of the prostate is called benign enlargement of the prostate. So in case of benign enlargement of the prostate, we need to do prostatectomy or transurethral resection of the prostate. This operation also need continuous irrigation of the urinary bladder, that so that it remains clean and no infection effects. So TURP, that means transurethral resection of the prostate, is also needs 0.9% sodium chloride solution. Medical use as a nasal decongestant, especially in case of neonate and children, they also use 0.9% sodium chloride solution. In case of nebulization, along with the respiration solution, who have seen nebulization in an asthmatic patient? Anyone who have seen the nebulization process? Have you seen ever?
No, sir.
Okay. So nebulization is a process along with respiratory solution like salbutamol. In case of asthma patient, we give nebulization therapy. Salbutamol, ipratropium bromide, normal saline is used in the acute severe bronchial asthma, as I was saying, and COPD, that means chronic obstructive pulmonary disease. So we use this 0.9% sodium chloride solution. That's all for today. I think in the next class we will discuss about the rest things. We have remaining molar solution definition and osmolar solution, plasma osmolar gap, osmotic gap, all those important things we need to learn. We need colloid, we need to learn difference between the colloid and crystalloid. We need to learn all those. Inshallah, this will be discussed in the next class. Also, we need to discuss about the dialysis, which is one of the most important things. Gives donor membrane equilibrium. This is also important. And active transport, passive transport, all discussed in the physiology. This will be easy, inshallah. So, see you in the next class. Thank you all. Thanks for the